Okay, so I've got the wave ready to go. I'm going to press the timer button. And what we're going to do is we're going to make one complete wave. We're going to calculate its wavelength, and we're going to calculate its period. So let's go. One wave going. And there we go, 0.4. And we can measure the wavelength. There we go. And then that. So if we start at 0 and we end approximately there, we can say that's approximately 2.5 centimeters. And here from this measurement, we can get the period time is equal to 0.4 seconds. Now we've got to really think critically, and we've got to ask ourselves, what is it that's actually moving? What are we saying? What are we saying moved from? I'm gonna draw it over here in, let's use a nice color that you can see over here. Oh no, you can't see that. Let's draw it. Choose a color. Oh no, that doesn't work. Let's take blue. Blue is different. Okay, something starts over here and now it's over there. Ooh. What is it that moved? Did any of those individual beads move? So if you look at the individual beads, did any of them physically move from left to right? Guys, give me a second. You could, yeah. Did any of the beads physically move? So what you'll see is that the beads are actually just moving up and down. They're oscillating in a fixed position. Cool. So I'm going to quickly take you back to this, and I'm going to go to manual, and I'm going to show you what is it that I'm doing to the wrench.
You're moving it up and down.
Correct. And when I talk about movement and in terms of energy, what kind of energy?
Kinetic.
Kinetic energy, correct. So when we look at our wave, and we ask ourselves, what is it that is moving? What is it that's moved the distance of the blue arrow?
The kinetic energy.
Correct, the kinetic energy. The kinetic energy, or the work done, has been moved. In other words, the oscillation started at the left-hand side, and the energy now has reached that green ball. And you can see, and you'll see later when I carry on, the next ball to move is going to be that green one. But would you agree with me that these balls over here, these ones over here, have no kinetic energy yet, because the wave hasn't reached them? Cool. So in terms of wave movement, what is actually moving? I just said the answer. You can just say it for yourselves. What is actually moving? You can say it.
Energy.
Kinetic energy, correct. So it's the kinetic energy that's moving. It's not the wave itself that's moving. It's the energy that's moving along the wave. So when we ask ourselves, what is the speed of a wave? What we're actually asking is, how fast is energy being transferred along that wave? Cool. So how fast is energy being transferred along the wave? Okay, so let's just think of a basic speed equation. Forget about waves for a second. What is just a basic speed equation? Forget about the waves. Cool. What's a basic speed equation?
Distance divided by time.
Correct. So if I say that velocity is equal to distance divided by time. Now what we can say is, in terms of the energy, what distance did it travel and how long did it take? So have a look. I'm going to just point it out quickly. This length of that arrow, what's the length of that arrow?
One wavelength.
One wavelength, correct. Oh, I like the way you said it, one wavelength. And what is the t in terms of the bottom t? Not the value, but the meaning. What's the meaning of the bottom t? How long did it take to get there? And what do we call that? Time, correct, which is called the?
Period.
Period, correct. So we have the wavelength divided by the period. And then we can finish the calculation and we can say that it's 2.5 centimeters. And we can
Which
say
is
that
kind of
it's-
like distance over time.
it's exactly distance over time. It's precisely distance over time. So 2.5 divided by 0.4. I got my calculator just for this reason. 2.5 divided by 0.4, and that gives 6.25. So 6.25, and that's centimeters per second. In other words, the energy of the wave is traveling at a speed or a velocity of 6.225 centimeters per second. Does that make sense? Cool. So the speed of the wave is 6.25 centimeters per second. Okay, so let's restart, pause, restart the timer, restart the wave. Now we're going to keep amplitude the same, and what we're going to do is we're going to change the frequency. So we're going to change the frequency from 2.5 to 1.25. So we're going to exactly half the frequency. We don't have to halve it. We're just choosing a nice number because it'll probably work out nicely. So I start my timer. It's on play pause mode, and then I can start creating the wave. And now I want to make sure that I create exactly one full wave. So there we go, 0.8. Does that kind of make sense when you forget about all the rest? Would you agree with me that when I halve the frequency, I double the period? Cool. Yep, good. And then we can do the measurements. There's the one. We can do the second measurement, that's there. And we can say that the wavelength is equal to 5 centimeters. The period is over here. The t is equal to 0.8 seconds. And then we can do the calculation here in the bottom right and left-hand corner. Speed is equal to distance over time is equal to wavelength over period, which is equal to 5 centimeters divided by 0.8. And that gives you, can anyone guess the answer without me having to say it, without me having to do the calculation? If you don't remember the value, can you remember the old one? In relation to the old value, do you think it's bigger, smaller, or the same?
Would it be that this?
It's the same, correct. So if you do the calculation, 5 divided by 0.8, it's 6.25 centimeters per second. So let's have a look. If we go there, for the first wave, when the frequency was 2.5, the period was 0.4. And for the second wave, when we halved the frequency, we doubled the period. So would you agree with me that at the top, I doubled the number, and at the bottom, I halved the number? No, other way around. At the top, I doubled the number, and at the bottom, I also doubled the number. So if I double them both, you get the same value. So 2.
So you said, never mind, sorry, continue.
Cool. So 2.5 divided by 0.4, have a look what happens. I get 5 divided by 0.8. I've doubled the top and I've doubled the bottom. So I've doubled the wavelength and I've doubled the period, which means that the speed stays constant. Cool. So the speed of that wave is the same. Cool. Any questions?
No, sir.
No, you good? Everyone happy with that? Guys, you got to stop me. If it's confusing, you have to stop me. You have to tell me now. It's no use you sitting there confused and you don't know how to ask the question. So if you're confused, say something. Good, cool. Okay, so you're happy with the fact that we can calculate the speed of the wave based on the wavelength and the period. Can someone quickly erase, I don't know who's drawn lines on the screen. Can somebody just erase that quickly? It's not me as far as I know. No. No, not that. There's red lines. Can you see the red lines at the bottom?
Yes,
Yeah.
sir.
Yeah, that's not me.
Yes, sir.
That's somebody else's somewhere.
No,
and
and I can't, so I
Mm-mm.
don't know.
Okay, but I can
Well,
erase
Okay.
it, so that's fine. There we go. So it doesn't matter. It's fine. It's gone. Okay, so what we're going to do now is we're going to say, well, calculating the period is difficult because calculating the period means I need to use the timer. So what we're going to say is, what is the relationship between period and frequency? And then instead of using the period, let's use the frequency to calculate the period of the wave. So let's restart. Restart that. And let's go restart. And let's play. So what we're going to do is we're going to make a lot of waves and we're going to count the waves and we're going to divide them in two different ways. So let's have a look. Let's create two waves. It's one wave. That's 1.5 waves. That's 2 waves. I'm going to get rid of the rulers because I don't need them. I forgot to press timer. So start the timer and go. Go, 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 go. Here we go. Okay, so this is going to be a little bit of mathematics, meaning we're just going to divide the numbers, but we're going to divide them in two different ways. Cool. So we're going to say that it was two waves in 0.8 seconds. And what we can do is we can take the seconds and divide it by the waves, or we can take the waves and divide it by the seconds. So what do you want to do first?
The waves, I mean the seconds divided by waves.
Okay, perfect. So we do seconds divided by waves. So you can do seconds over waves. And that's 0.8 seconds over 2. And I'm going to leave the 2 unitless because waves are not technically a unit that we measure. They're just something that we can count. We can count the number of waves. So 2 in this case is just a number. It's a unitless quantity. We're not saying wave is a unit. We're just counting there's 2 waves. 1, 2. Cool. And that gives you 0.4 seconds. And which quantity is that? What if we calculated the 0.4?
That's the period now.
Correct. That's the period. So that is the period T. Cool. So that's the period of the wave. Cool. But what I'm going to show you now is we can take those exact same numbers. We can take those exact same numbers and we can say 2 waves in 0.8 seconds. And instead of taking the seconds and divided by the waves, we can take the waves divided by the seconds. So we can say waves.
No, the frequency.
Correct. Seconds is equal to 0.8 seconds over, no man, idiot, undo, 2 waves and 0.8 seconds. And that gives you 2 divided by 0.8. Yeah, the answer is at the bottom of the page, 2.5, and it's seconds to the -1. Cool, and you're correct, Gloria, that's called the frequency, correct. So how many waves do I get per second? I get 2.5 waves per second. And where have you seen the 2.5 before? It's on the page.
In the frequency thing?
In the frequency thing, correct. So I set the frequency to 2.5. So I actually haven't measured the frequency. All I've done is I've confirmed. Ooh. So this is just confirming that the frequency is 2.5 because it's the number of waves per second. So if I take waves divided by seconds, I get the frequency. And if I take, in the previous example, if I take seconds divided by waves, I get the period, and that's just time, the amount of time taken for one wave to pass. Cool, everyone happy with that?
So why don't we write it in hertz Why do we just say second per second for the frequency thingy?
Very good question. We wrote it like that because we hadn't introduced the unit yet. So Stefan is absolutely correct. What we've learned now is that the seconds to the -1 is basically what we call the hertz. So hertz is just like a nice name, you know, like some like Newton and Pascal and Joule and all these fancy things. Per second just has a fancy name, and that fancy name is hertz. But in actual fact, in SI units, a hertz is a per second. So in SI units, it's per second. In named units or nice units, it's hertz. Well, but you know, you can take any quantity and convert it to SI units. You don't have to give them names. You can write them all in kilograms, meters, and seconds. Cool. Everyone happy so far? Any questions on that?
No.
No, good. Okay, so this what I'm going to do now is it's literally on the Google Classroom, and instead of rewriting it, I'm just going to open the PDF and I'm just going to walk you through it. So I'm going to show you on the PDF the manipulation that you need to do. So all of the stuff we did is here. There's talking about wavelength. There's talking about change in frequency. There's talking about the period, frequency, change in frequency, relationship between that. Here we go. This is the important one. Okay, so if 3 waves are formed in 1 second, the period is the seconds divided by the waves, and the frequency is the waves divided by the seconds. Everyone happy with these two statements over here?
Yep, sir.
So we have period and we have frequency. Now the slightly more mathematical one is, would you agree with me that they're just the inverse of each other?
Mm-hmm.
Yeah. So if I took either one of those two quantities and I inverted them, I would get the other quantity. How do I delete that? Delete. Go and delete that. Cool. Does anyone want me to go through that in terms of the maths, or are you happy with that? Just shout quickly. Would you like me to go through the maths of that equation? No? Everyone good?
1 over 2.5 is 0.4, so
Exactly,
yeah.
correct. 1 over 2.5 is that. But in terms of just the manipulation, forget about the things that we can add to it. Just in terms of the variables, are you happy with the fact that they're inverse of each other? So in other words, if I take t to the -1, it's equal to the frequency. And if I take f to the -1, it's equal to the period. Sorry, those two are in the wrong place. That's not supposed to go there. That's supposed to go there. T is equal to frequency to the -1, and frequency is equal to t to the -1. Guys, please stop me. If you're not happy with that, I need you to tell me. So I'm going to guess everybody's happy with that. That's good. Excellent. So that's just a bit of math. Okay, then we can go back to the speed of the wave. This is at the bottom here somewhere. There we go. Okay, so recall that speed is equal to distance divided by time. In the case of the energy, remember that for a wave, it's the energy that's traveled. The distance traveled is equal to the wavelength, and the time taken to reach that point is the period. So up until this point, we have this equation, speed is equal to wavelength divided by period. Cool. In general, speed is equal to wavelength divided by period. It's equal to that. And then here's an interesting thing. You can break those two things apart, and you can write it as wavelength over 1 times 1 over t. So I've just broken that apart. I've taken this, and I've said that this is lambda over 1, and I'm multiplying it by 1 over t, because multiplying by 1 over t is the same as dividing. Cool, and then recall that we have a relationship between frequency and period, and therefore we can solve for the wave equation. The velocity of the wave is equal to the wavelength times the frequency. Cool. Everybody happy with that? Good. Get rid of that. And get rid of that. And get rid of that. Good, good, good. Okay. So in other words, we don't need to calculate the period every time. We don't have to time the wave. If we do a calculation on the simulation, we can get rid of the timer. The only thing we need out is our ruler, and we can measure the speed of the wave. So we can let the wave go for a little while, press pause, and then we can do the calculation. So we can measure the length. So from there to approximately there, let's call that 2.5 centimeters. That's the wavelength. And then we can just read off the frequency at the bottom here. So here's the frequency F. In other words, the speed of the wave is equal to the lambda times frequency is equal to 2.5 times by 2.5. And that gives you the 6.25 that we had last time. Yeah, it's the same. It hasn't changed. So it's still equal to 6.25 centimeters per second. Cool. Everybody happy with that?
Yes,
Good, good, good. And then you can change the frequency. You can change it to, let's say, 1.25. In fact, let's use an ugly number. Let's change the frequency to an ugly number. Let's change the amplitude. And then now we've changed two variables, obviously, which we shouldn't do, but we're changing two variables, but we're still going to see, can we confirm that the speed of the wave hasn't changed? Pause that. Oopsie, I can't do that. I have to put the ruler on first where I want to measure. Let's measure from that point to that. There we go. Okay, so I can measure from there.
sir,
You know,
if the speed of the wave always stays constant, what
Correct.
again will make it change? If
what will change the speed of the wave?
yes,
I'll show you just now. So
Okay.
we'll see now how you can change the speed of the wave. So the lambda is equal to 4.2. So the velocity is equal to lambda times frequency is equal to 4.2 times by, we can read the frequency 1.44. So 4.2 times 1.44. And remember there's uncertainty involved. So we're not going to get an exact answer. It's 4.4.
actually,
It's 4.4. Yeah. Sorry. Yes.
Actually, now I understand why it doesn't matter, because the amplitude doesn't affect the wavelength. So
Correct.
anyways, you only in the frequency.
Exactly.
Okay.
Because we already confirmed that the frequency doesn't affect the wavelength. If the wavelength doesn't change, it's only the frequency and the wavelength that interplay. If the one gets bigger, the other gets smaller, and it balances out for the speed. Sorry guys, it's 4.4. Not 4.2. I read the scale wrong. So I got the incorrect answer and I wasn't sure why, and now I know why. And it's 6.33336, which is close enough to 6.25. The old one was 6.25. But remember, there's uncertainty involved in the way that I'm measuring my wavelength. So that's creating a tiny bit of uncertainty. But would you agree with me that it's more or less the same? Would you agree with me? Yeah, everyone good? Nobody agrees with me?
More or less the same.
More or
sir.
less the same. Yeah. And when I say more or less the same, now I want you to think of paper 3. This could be a paper 3 question, who knows? But I want you to think of paper 3 question 1. Paper 3 question 1, in other words, the one where you draw the table. What would you do to investigate the speed of the wave in terms of its frequency and its wavelength? What would you do? Somebody just quickly say that, tell me, what would you do in terms of frequency and wavelength? What would you do to calculate the speed of the wave? In terms of paper 3 question 1. So not alternative, the advanced practical skills. Paper 1 is where you draw the table. Then you do something with the table, manipulate the data, and you come out with an answer. What would you do with this data in terms of frequency and wavelength?
So are you asking what the practical would be?
Exactly. What would the practical be? So how would you investigate the speed of the wave? Would you only do the calculation once? Would you measure one frequency and one wavelength?
Probably different.
Correct. So
times-
what would you do in terms of what would you change and what would you measure? So if you're playing with the app, so think of it in terms of a question. You need to change one thing, and you need to measure another thing. So on the app, what is it that you can change and what is it that you can measure?
You change the frequency.
Correct, we can change the frequency. We have total 100% control over the frequency. We're allowed to change it to whatever value we want. Cool, and then what is it that we always measure on the app in terms to calculate the speed?
Wavelength.
The wavelength.
Correct, so wavelength. So wavelength is what we would measure. Cool. So frequency f and wavelength lambda. Cool. Then what you could do is you could tabulate it in terms of frequency and wavelength. And then you can think about plotting a graph of what is it that you're going to change. Wait, let's just think about this quickly. We'll have wavelength over here and we'll have frequency over there. Now the problem with this is that if you think about it, if I find the gradient of that graph, what's it going to be? Just think about the gradient, forget about everything else. What two values would I divide it by to get the gradient?
Lambda over frequency.
Correct, lambda over f. And in terms of the speed of the wave, speed is equal to lambda times frequency. So would the gradient of that graph be the speed?
Yeah.
No.
Oh,
Because-
dividing the.
Because exactly,
the
this is
frequency.
divide and
That's
this
multiply.
is multiply, correct? So it's divide and multiply. So in other words, if I was going to plot a graph, if this was lambda, what do I need to plot here, question mark, in order to get a straight line where the gradient is equal to the speed is equal to lambda times frequency? What would I have to plot on the x-axis?
T.
T, correct. And what is T in terms of frequency?
What the period?
Correct. What's the relationship between period and frequency?
They're inverses.
Inverse, correct. So that's 1 over f.
Mhm.
So if you plotted a graph of lambda versus 1 over f, you would get a straight line. The gradient of the graph would be that. Now I'm going to do a double divide, 1 over f. The 1 over f is negative at the bottom, so it's going to come to the graph top, and then the gradient is going to be equal to lambda times frequency, which is equal to the speed. There you go. So in other words, what you need to do, this is basically the summary, this is the sort of final take-home message, is you need to play with the app. You need to change the frequency in hertz. You need to calculate the wavelength in centimeters. Sorry, this is change. This is measure. Cool. You need to put a table, you need to put a column for 1 over, no, idiot. You need to put a column for 1 over f, which is actually just seconds. And then you're going to plot a graph of wavelength over 1 over f in seconds. That's obviously centimeters. And then you'll find a straight line with gradient speed. Cool. And that'll give you a nice result, because what it'll do is it'll smooth out all the uncertainties. And instead of saying, I'm going to base it on 2 different calculations, I'm going to base it on, let's say, 6 different calculations, and I'm going to take an average. So that's what the line graph is essentially doing. The line graph is saying, obviously, because of uncertainty, we're not going to get exactly the same value each time. But if I plot the graph, what I'll find is, let's think of a graph, it'll look like this. The data won't be perfect, but if I wanted to, I could plot the straight line and I could do that. Cool, makes sense?
So what type of practical would this be? Like, what would you do as like
What
the
would you
experiment?
do? So for example, I can't think of one at the top of my head, but if you think about all those oscillation questions where they give you like pendulums and stuff, would you agree with me that very often they ask you to calculate the period? So they often ask you to calculate the
Yeah.
period. Yeah, but when they ask you to use the data, they often ask you to leave a column for 1 over t. Would you agree with me?
Yeah,
Like,
yeah.
when they ask you to plot the graph, they don't ask you to plot a graph of what you change to t. They often ask you to plot 1 over t, which would you agree with me is the frequency? Yeah, so basically what they're saying is that all of these calculations can be done in one step. In other words, I can literally take any data point, and from that data point, I can say v is equal to lambda over t. And I can do that for every single one. But would you agree with me that they're not all in the same straight line as far as they're drawn over here? I mean, as far as they're drawn here, are they all on the same straight line? Do they fit the line?
No.
Also, if I call
Don't
this one
fit.
V1 and if I call that V2, V1 is not going to be equal to V2. But would you agree with me that the ideal situation is that without uncertainties, they would all fit on the straight line? So without uncertainties, they should all perfectly fit on a straight line.
Mm.
And that's the whole point of doing the practical. That's the whole point of doing paper 3. Paper 3 question 1 is basically saying, well, you could literally just find one oscillation and change the length 1, find the oscillation and just do a calculation and get a value. But you can't trust that value because you've only done the calculation once. So you vary the one thing, you measure the other, and then you plot a graph of those two and you find out whether there's a relationship or not. And if there is a relationship, they should form a straight line. Okay, so what you're going to do is you're going to play with the app like this. You're going to take the PHET sim. And now what you're going to do is you're going to change the tension. And just have a look. I'm not going to change anything else, but have a look what happens to the wave when I change the tension. So when I change the tension, I change that. But would you agree with me? I haven't changed the frequency. So I haven't changed the frequency. The frequency is constant. So if I change the tension, what's the only thing that's changing? What's changing when I change the tension?
It's the wavelength.
The wavelength, correct. And when you think of the equation, speed is equal to wavelength times frequency. If this is constant, and if I change this, would you agree with me that the speed is directly proportional to the wavelength? Meaning that if the frequency is constant, if it's the same number, if I constantly multiply by the same value, then what will happen to the speed if the wavelength increases?
It's also
going to increase, correct? And that's exactly what you're seeing happen here, is that I'm changing the tension, it's changing the wavelength, and if it's changing the wavelength, it's also changing the speed.
So you said that it's directly proportional to the frequency.
To both, it's directly proportional to both.
To both.
Correct.
If the wavelength changes and the frequency just stays the same.
Correct, 100%. So you have to keep one constant. You can't change two things simultaneously. Otherwise, you have to look at it as being like a square proportional kind of thing because you've changed two variables. Cool. So keep one variable the same and change the other. So what you're going to do is you're going to take this and you're going to change the frequency. Cool. Keep the tension the same. Don't change that. So keep the tension the same. Change the frequency and you're going to measure the wavelength. And then what you're going to do is you're going to say keep tension constant. So that's the tension, keep that constant. And then you're going to plot a graph, or you're going to make a table of frequency, wavelength, 1 over frequency. And then you're going to take that and plot a graph of wavelength over 1 over frequency. Cool. For one specific tension. This graph is only for one specific tension. In other words, it's constant tension. We're not changing the tension.
Okay, so keep the tension the same.
Keep the
and-
tension the same, and then basically measure the speed. Do I really need to plot the graph to measure the speed?
No.
No, because I can
No.
literally, yeah, I can literally do it from one calculation. But you saw from the previous example, I did the same calculation and I got two different values. And that's because I'm making uncertainties in my measurements, and it's specifically related to the ruler, because the ruler is so inaccurate or imprecise. It only gives me to the closest centimeter, or in fact to the closest 2 centimeters for that matter. Cool, happy days. So you're going to play with that, and then it's like normal. I'm not going to ask you to hand it in or send it as homework or whatever. You do it, and if you want me to check, you can send it to me as a WhatsApp image or a picture or whatever, and you can ask me to check it and see if it's okay.
So we only changed the frequency for this thing, right?
Correct. So you're going to plot a graph of frequency versus wavelength. And from that, you can plot a graph of wavelength on the y-axis and 1 over frequency on the x-axis. And then you should get a straight line graph, and the gradient will be the speed.